This lecture is about the mixture of Unigram language models. In this lecture, we will continue discussing probabilistic topic models. In particular, we're going to introduce a mixture of Unigram language models. This is a slide that you have seen earlier, where we talked about how to get rid of the background words that we'll have on top of estimated language model for one document. So if you want to solve the problem, it would be useful to think about why we end up having this problem. Well, this is obvious because these words are very frequent in our data, and we are using a maximum likelihood estimate. And then the estimator obviously would have to assign high probabilities for these words in order to maximize the likelihood. So in order to get rid of them, that would mean we have to do something different here. In particular, we have to say that this distribution doesn't have to explain all the words in the text data. Or we're going to say these common words should not be explained by this distribution. So one natural way to solve the problem is to think about using another distribution to account for just these common words. This way, the two distributions can be mixed together to generate the text data, and we'll let the other model, which we call background topic model, to generate the common words. This way, our target, the topic theta here, would be only generating the content words that characterize the content of the document. So how does this work? Well, it's just a small modification of the previous setup where we have just one distribution. Since we now have two distributions, we have to decide which distribution to use when we generate the word. But each word will still be sampled from one of the two distributions. Right? So text data is still generated in the same way. Namely, we're going to generate one word at each time, and eventually we'll generate a lot of words. When we generate the word, however, we're going to first decide which of the two distributions to use, and this is controlled by another probability of theta sub d and the probability of theta sub b here. So this is the probability of selecting the topic word distribution. This is the probability of selecting the background word distribution denoted by theta sub b. Now in this case, I just gave an example where we can set both to 0.5. So you're going to basically flip a coin, a fair coin, to decide which one to use. But in general, these probabilities don't have to be equal. So you might bias toward using one topic more than the other. So now the process of generating a word would be to first to flip a coin based on these probabilities of choosing each model. And if, let's say, the coin shows up as head, which means we're going to use the topic word distribution, then we're going to use this word distribution to generate a word. Otherwise, we might be going through this path, and we're going to use the background word distribution to generate a word. So in such a case, we have a model that has some uncertainty associated with the use of a word distribution. But we can still think of this as a model for generating text data. And such a model is called a mixture model. So now let's see, in this case, what's the probability of observing a word, W. Now here I showed some words like the and the text. So as in all cases, once we set up the model, we are interested in computing the likelihood function. The basic question is, so what's the probability of observing a specific word here? Now we note that the word can be observed from each of the two distributions. So we have to consider two cases. Therefore, it's a sum over these two cases. The first case is to use the topic word distribution to generate the word. And in such a case, then the probability would be the probability of theta sub d, which is the probability of choosing the model, multiplied by the probability of actually observing the word from that model. Both events must happen in order to observe the. We first must have chosen the topic theta sub d, and then we also have to actually have sampled the word the from the distribution. And similarly, the second part accounts for a different way of generating the word from the background. Now, obviously, the probability of text the same is all similar, right? So we also consider two ways of generating text, and in each case, it's a product of the probability of choosing a particular word distribution multiplied by the probability of observing the word from that distribution. Now later you will see this is actually a general form, so you might want to make sure that you have really understood this expression here, and you should convince yourself that this is indeed the probability of observing text. So to summarize what we observe here, the probability of a word from a mixture model is in general a sum over all different ways of generating the word. And in each case, it's a product of the probability of selecting that component model multiplied by the probability of actually observing the data point from that component model. And this is something quite general, and you will see this occurring often later. So the basic idea of a mixture model is just to treat these two distributions together as one model. So I used a box to bring all these components together. So if you view this whole box as one model, it's just like any other generative model. It would just give us the probability of a word. But the way it determines this probability is quite different from when we have just one distribution. And this is basically a more complicated mixture model. Sorry, a more complicated model than just one distribution. And it's called a mixture model. So as I just said, we can treat this as just a generative model. And it's often useful to think of just the likelihood function. The illustration that you have seen before, which is dimmer now, is just the illustration of this generative model. So mathematically, this model this is nothing but to just define the following generative model, where the probability of a word is assumed to be a sum over two cases of generating the word. And the form you are seeing now is a more general form than what you have seen in the calculation earlier, where I just used a symbol W to denote any word. But you can still see this is basically first a sum, right? And this sum is due to the fact that the word can be generated in multiple ways, two ways in this case. And inside the sum, each term is a product, again, of two terms. And the two terms are first, the probability of selecting a component like theta sub d. Second, the probability of actually observing the word from this component model. And so this is a very general description of, in fact, all the mixture models. And I just want to make sure that you understand this, because this is really the basis for understanding all kinds of topic models. So now, once we set up the model and we can write down the likelihood function, as we see here, the next question is how can we estimate the parameter, or what to do with the parameters given the data? Well, in general, we can use some observed text data to estimate the model parameters. And this estimation would allow us to discover the interesting knowledge about the text. So in this case, what do we discover? Well, these are represented by our parameters. And we have two kinds of parameters. One is the two word distributions. Those are two topics. And the other is the coverage of each topic in the coverage of each topic. And this is determined by probability of theta sub d and probability of theta sub b. Note that they sum to 1. Now, what's interesting is also to think about the special cases, like when we set one of them to 1, what would happen? Well, with the other would be 0, right? And if you look at the likelihood function, it will then degenerate to the special case of just one distribution, right? So you can easily verify that by assuming one of these two is 1.0 and the other is 0. So in this sense, the mixture model is more general than the previous model, where we have just one distribution, and it can cover that as a special case. So to summarize, And we talked about the mixture of two Unigram language models. And the data we are considering here is just still one document. And the model is a mixture model with two components, two Unigram language models, specifically theta sub d, which is intended to denote the topic of document D, and theta sub b, which is representing a background topic that we can set to attract the common words, because common words will be assigned high probabilities in this model. So the parameters can be collectively called lambda, which I show here again. And you can again think about the question about how many parameters are we talking about exactly. This is usually a good exercise to do because it allows you to see the model in depth and to have a complete understanding of what's going on in this model. And we have mixing weights, of course, also. So what does the likelihood function look like? Well, it looks very similar to what we had before. So for the document, first it's a product over all the words in the document, exactly the same as before. The only difference is that inside here, now it's a sum instead of just one. So you might recall before we just had this one there. But now we had this sum because of the mixture model, and because of the mixture model, we also have to introduce a probability of choosing that particular component distribution. And so this is just another way of writing it again by using a product over all the unique words in our vocabulary instead of having a product over all the positions in the document. And this form where we look at the different unique words is a convenient form for computing the maximum likelihood estimate later. And the maximum likelihood estimate is, as usual, just to find the parameters that would maximize this likelihood function. And the constraints here are, of course, two kinds. One is the word probabilities in each topic must sum to 1. The other is the choice of each topic must sum to 1.